Modern programming languages are often quite frivolous when it comes to immutability. For example, C++ allows you to remove const-ness at any moment. Java removes that final attribute with reflection. Rust has the concept of interior mutability. Even if constancy is supported in some form, it's limited to a single field or variable. Or move from compile-checked invariants to runtime checks, which damages application resilience. In some GC-based languages, there is the concept of an immutable reference to an object, but not the reference to an immutable object. The honest, true, and complete support for immutability must be built into the language. Argentum takes immutability very seriously. It has a special type, reference to immutable object, and a special class of methods that cannot modify the object on which they are called. Here icon owns the immutable surface instance. And here this function returns an immutable surfaces. This method can be called on both mutable and immutable instances. Frozen objects are created with a prefix *freeze operator, which creates an immutable copy or, if safe, freezes the object in place. It's like build a pattern, we create a mutable object, fill its properties, and then freeze. Unlike other languages, you don't need to create parallel mutable and immutable versions of your classes. Objects get frozen per instance. The main reason for frozen objects is safe at-scale data structures. But the key side effect is easy sharing between data hierarchies, threads, and distributed systems. Thus, references are also shared, aggregate references. Here we have 2 pointers to the same string. And 2 bit fields pointing to the same surface. When copy operator applied to an object having fields, it doesn't copy, it shares. If copy operator applied to a frozen object, it returns a mutable copy with a new ownership. Here we take a frozen object, make its mutable copy, modify it, and freeze it again. Notice how other references keep pointing to an old object. There is no accidentally sharing of changes between object hierarchies. The value of the immutable object's hash function is guaranteed to be stable. That is why all key-value containers in Argentum have immutable keys. This is another safety measure that no other language has. We can imagine Argentum data structures as a tree of mutable objects interconnected with a web of weak links that reference a directed acyclic graph of shared immutable objects. Shared immutable pointers are leak-proof. We cannot assign to a mutable object a pointer to itself, because it's immutable. When an object is still mutable, there is no shared pointer to it. So, there is no way to create pointer cycles. As such, Argentum shared objects can be handled with a simple reference counting, and as we see later, not even using atomics.